All right. Hello, everybody. Can you hear me? Cool, cool. So let's get started. So hi, everybody. I'm Daniel Gergely. I'm an Android engineer at Tier, and I will talk about how we cleaned up state handling in our application using a state machine so that maybe you will get some ideas or some inspiration to your own projects. So we are a micromobility company, and we have an app that offers small electric vehicles to rent by the minute, such as electric scooters, electric mopeds, and electric bicycles. And we had some challenges regarding state handling, and more specifically, they were gathering around the so-called ride state. And to give you some context about what we call ride state, I would like to invite you to a time travel to the beginnings of our application, because at that point, it was really simple. Basically, the application only had two states. One of them on the left was kind of the default state. Then you could be able to see the map, browse the vehicles, look for one to start a ride with, and then you could start a ride. And then you would get to this other state on the right, where you could interact only with the one vehicle that you are in possession of for that time. And then eventually you could end the ride, and you would get back to this default state. And if you look at this from a pragmatic point of view, you can see just how simple that was. And I really want to emphasize that, because at these simple times, it was perfectly reasonable to go with a really simple solution and not to implement anything complex or sophisticated. And yeah, what we had worked pretty well. It was happy times. But then a product came to us and asked if, hey, could you implement this feature called pause ride? Then we said, yeah, sure. So what happened is that the set of states kind of expanded. By the way, what a pause ride means is that the vehicle is locked, but it's still at your rental, still in your possession. You still pay for it, and you can just then resume it. It comes really handy when you have to go to a store and pick up something. And then we also introduced a really cool feature called user battery swapping. What it basically is that it allows the users to go to a swap spot where there's this power box, and then take out the depleted battery of the vehicle and swap it with the charged battery from the power box. And it helps us, it helps the environment, and also the users get rewarded for doing it, so it's really a win-win kind of situation. And then we were thinking about, what if we added a feature that could, in some cases, offer rides completely free of charge for the users in case they were willing to go to a swap spot and swap the battery. And it's really a good idea, but what it would also imply is that the set of states would expand even further. And then we were thinking that, what if we added a feature where user could select a vehicle from the map that is further away, and they could reserve it for themselves, so while they walk to it, other users won't steal it from them. And what that would mean is an even more complex state space. So at that point, when we were trying to think of how we would implement these new features, we unfortunately ran into some problems. Namely, that our code was kind of a natural evolution from a small to large set of features, and it was becoming less maintainable, it was becoming harder to read, it was becoming harder to contribute. It was also, at that point, really hard to introduce any new ride features. So at that point, what we did is just, at first, to try to sit down and try to find out what the exact problems are. And what we came up with at that point is that our major problems were, we had no clean representation of ride states, we had no single source of truth. About that, there were just a lot of callbacks going around, and finally, the flows were hard to extend, which is kind of a symptom of the first two. So to get into these a little bit more deeper, let's start with the lack of clean representation of ride states. So as you can see, what we had at the beginning was one flat class with a lot of fields. Most of them were nullable or optional, such as if the state is a reservation, when did the reservation start? If this ride has already started, when did it start? And if this ride had already finished, what is the final class? And one problem that is almost screaming from the screen is that we need some subclasses. And there was another problem, which is maybe not so obvious, but also super important, is that you might have noticed that actually I didn't give you an exact definition of what right state means for us. And the reason for that is that up until this point, we didn't actually know. We didn't actually ask the question, what is the right state? And as we were looking, especially that field, the final cost, which is something that is only available once the ride has already ended, it became apparent to us that at that point, we have no clean boundaries of states. We have no clean scope defined what should right state mean. And the reason for that is that ride model basically contained a state called ended ride. And it was necessary because, as I said, it contains some crucial information, such as the final price, which obviously can only be calculated once the ride is done. And it makes sense from a data or product point of view, because at the end of the day, the life cycle of ride contains this ended ride state. But if you think of it from an application behavior point of view, how does the app behave? How does the app look like? What can you do with this app? Then you start to see that it doesn't actually make sense to have an ended ride state, because if you think of it, the no ride and ended ride are pretty much the same. So we decided to exclude this ended ride from the set of states. And how we handle that data, I will circle back to that later. But now, as we had a clear picture of what the issues are, it was time to gather around the whiteboard and start to design some solutions. So first problem that we tackle is now finally to have a proper domain representation for right states. And as a first step, yeah, we had to define some clean boundaries, and we stick to that definition that we should be representing the behavior of the app. So we removed any fields that was related to this ended right state. And also, we had to create some type hierarchy to represent our states. Basically, in this case, you have a lot of options to choose from. You can go with a sealed class, you can go with a normal abstract class or interface. Basically, just do whatever works for your project. We ended up with a fairly regular sealed class. And one thing I was really happy about is that the ratio of nullable fields has dropped significantly. I was happy to see way less question marks, both figuratively and literally. So we were really happy with this design. And to go back to our problems, we still have two problems to have a design to tackle. One of them is no single source of truth. And at that point, we agreed on that whatever solution we might have in the future, it should definitely have a single source of truth, have a single entity that owns the state. And for extensibility, we agreed on that we should make something scalable. And what it meant particularly for us is that there should be no single class that keeps on growing as you add more and more new features, because that is exactly the recipe for a God class, and we wanted to avoid that. And as we were looking at these 2 points, it felt challenging at that time to come up with something that satisfies both of these criteria. But at that point, we remembered something that everybody learns in college, but later tends not to use it. And it was, of course, a state machine. So to have a state machine, you obviously need to have a set of states, and we already had a design for that we were satisfied with. And at that point, we introduced another term to our nomenclature, which was actions. What an action is, for us, is basically a user-initiated state change in write state. So an action has an input, which is the old state, the current state that the user wants to transition out of, and it has a main input, which is the new state that the user wants to be in. And it also has another output, which we named a result, which can contain any additional data that is necessary for us, but is outside the state handling boundaries. And it was really useful when we modeled Android. And if we take a look at the code representation of this action, now it is fairly straightforward. It's become a generic abstract class with a function that as an input takes the current state and as an output returns composite object consisting of the new state and this result object. And by the way, as you can see, here we are using RxJava. The reason for that is that we have RxJava throughout our application, but this concept could work with coroutines or even synchronous functions. So to look at an example implementation of an action, this is how the Android could look like. As you can see, it's fairly simple to implement an action into this framework. We would just inject our API client, take some data that we need from the current ride, submit it to the API, and once we have the result, we know that the new state would be no ride, and the result we can just map from the network response. So now that we have a definition for the states and also the actions, now it's time to think of the glue that would hold this all together. And that would be, of course, the state machine itself. And how we decided to tackle it is to, at first, just create a buffer that would hold our write state. We just used, at first, a behavior subject for that. And to actually perform any actions, we exposed the function in our state machine that would take in an action object as a parameter, and how it would actually deal with it is at first fetch the current state from the buffer, and then feed that current state to our action object and perform the action. And at that point, if it was successful, we would save this new state to our buffer, and we would return the result object that came out from it. And as you can see, there's really no error handling here, and the reason for that is that we just relied on RxJava's onError branch to make sure that whenever an action were to fail, in that case, the write state wouldn't be updated. And yeah, at that point, we had all these designs on a whiteboard, basically. We really liked it. We thought it could work. But then came some tough questions, is that how would we take this design from the whiteboard and actually put it to our code base? And it seemed challenging for us, because at Tier we have multiple teams that are working on multiple areas on the app, creating new features or making existing ones better. And for that reason, we have a frequent release cycle to make sure that we can get these changes to the users pretty quickly. And what that meant for us is that we couldn't just stop the word. We couldn't say that, hey, please don't release for 3 or 4 weeks because there's this big refactor that we need to get done. And we also couldn't introduce any large pull requests, because obviously that would carry risks. These are hard to review, and we would have to be rebasing or resolving merge conflicts all the time. So really, the only choice we had left is to introduce these changes incrementally. And for that, we collected our steps. First, we need to implement the refactored state model into the code. And it was actually fairly simple, as it was a refactor that could be taking place in only one pull request. Then we would need to add the implementation of the state machine. And this was actually even simpler, because what we needed to do at that point is to add this new write state machine class, but without any touch points to the application. So it was trivial. But then came the tough part, is that how would we migrate all the actions? Because what we needed to do at that point is that we had this ride repository, which was a monolith of a class containing almost all the ride features, such as start ride, pause ride, end ride. And what we needed to do is migrate all of these actions to be their own action class implementation. And then, of course, we could get rid of the old ride repository. And yep, this is something that obviously couldn't be done with one single pull request, with one step. So we needed to come up with something. And one option that came to our mind is something that I guess almost every one of you have already used in one of your projects, is to use a feature toggle or some kind of remote configuration. This is obviously a tool that allows you to ship a binary or ship parts of code that won't actually be used by the users or all users. And how it works is it requires you to add some branches to your code, basically, like if statements. And it works really well when you have to add new features, which only have maybe one or two entry points from your application, because then you have to place just a few if statements. But it can become really hard if you want to use feature toggles for modifying existing features in your application. You either have to add a lot of if statements, or you have to have a really smart abstraction layer, and you can introduce risks just by doing either of these. So what we ended up doing, rather than this, is we found a simple trick that we later referred to as hacking. Because what we did is we allowed these two components to coexist and introduced a sneaky pair of callbacks between them. And what they would do is that if the state changed on either of these components, this callback, one of these callbacks would make sure that the state would be updated in the other components. And as you can see, we definitely didn't want anybody to use this method for anything else. And what it allowed us to do is basically to migrate these actions one by one, and it allowed us to make these intermediate steps work. And yeah, in the end, we could migrate all the actions and get rid of the old ride repository and obviously the callbacks as well. So that's how we did it. To talk about the outcome, it was successful. We managed to pull it off with just a series of small pull requests. There were no increase in crashes or failure rates while the migration was going on. And as a bonus, it allowed us to implement follow-up improvements effortlessly, such as when we added a caching mechanism, it was only a matter of adding a few new lines to the code. So that was it. I would leave you with some takeaways. First is that whenever you are doing some kind of state handling, it's a good idea to, at first, define the scope or the boundaries of state handling clearly. And whenever you are doing any kind of refactoring, really, you should plan for incremental introduction, because what change at first could seem like a monster can be tamed just step by step. And this is useful, especially if you have some kind of hacky temporary solutions that you need to educate developers, other developers on the usage, so these methods or items won't get abused. So thank you for your attention, and if you have any questions, I am happy to answer them.